My name is Siddhant Mehrotra,
And I'm John McCormick.
and welcome to Applications of Le Châtelier's Principal Inquiry Lab.
Within the experiments, we're going to be testing the different effects of temperature, pressure, and concentration changes.
Okay, so there's going to be an inquiry lab with 2 parts each and a guided inquiry with 5 parts each. So I'll introduce the inquiry. So in part A, we're going to make a complex ion by testing the equilibriums of different solutions, and in the end you'll have a complex ion formed. And in part B, we're going to test the effects of temperature, so we're going to add heat and cold. Then in the guided inquiry of part A, we're going to make an acid-base indicator equilibrium. So there we're going to have an indicator, and we're going to test the effects of acids and bases being added and see the equilibrium that forms that.
And in activity B of the guided inquiry, we're going to be creating a copper complex ion. We're basically affecting the different amounts of concentration upon it and seeing the changes in equilibrium. In activity C, we're going to be doing, again, affecting a cobalt complex ions, except this time we're using more of not only concentration, but we're also going to be testing temperature with it to see the changes in equilibrium. In activity D, we're using the solubility of carbon dioxide, in which we're going to use pressure to change the equilibrium and to see what happens with it. And in activity E, we're going to be testing the solubility of magnesium hydroxide, which is also changes in specifically concentrations to see the effect of the equilibrium.
Okay, so get ready, and hopefully you'll learn something and you'll be able to be successful in your lab as well.
Have fun.
Thank you. Okay, so first, this is part A of the introductory, and we're going to first add 20 milliliters of the potassium thiocyanate solution, and it should be 0.002 molar. Okay, so you have a petri dish right here. So just make sure to observe what color it is. It's going to be clear. And then we're going to add 1 drop,
Three drops.
three drops of iron 3 nitrate. So make sure to use a clean pipette.
In different spots in the petri dish.
Different spots. 1,
2, 3.
Okay, so record the initial color, so that would be like a reddish orange right there.
Mm-hmm.
So right now the petri dish has the potassium thiocyanate and the 3 drops of iron 3 nitrate, and it's sitting there. So, and then it asks us to swirl it. So you put the lid back on, swirl your solution till there's a color evenly throughout. So now, that's about a lightish orange. Next step, you have to add half a pea size of potassium thiocyanate. So make sure you have the right crystals and you measure it out in a weighing dish. Half a pea size. Okay, so the crystals were kind of clear whitish, and the moment you drop them into the orange solution, it turns red, dark red. So
Then the directions say to wait 30 seconds and record after 30 seconds, and then after 30 seconds we'll swirl it and then record the color change.
okay, so after 30 seconds, the dark red has just spread out throughout, like around half of the petri dish, and then put the lid back on and swirl. So color is evenly distributed, and then observe. It's a darker red, almost like a cherry red, right?
I would say cherry red.
Yeah, cherry red. So as you can see, the iron nitrate reacted with the solution, and then when you added the crystals, the potassium thiocyanate crystal that reacted. So next, the procedure calls for half a pea-sized amount of potassium nitrate crystals in one spot. So your potassium nitrate crystals are the same white color. Add them to one spot. So initially there's no effect, but the procedure does say wait 30 seconds. So after 30 seconds, the crystals slowly spread out throughout the solution, and the solution gets a little clearer. Now keep your lid back on and swirl it. Got a little lighter, I think.
Looks like a metallic red.
Yeah. So it got a little lighter, slightly. So that's from your potassium nitrate crystals. And then now procedure calls for 1/4 pea size of sodium phosphate crystals, which are also whitish and grainy. So just in one spot, right? Yeah, so this is sodium phosphate monobasic in one spot.
And then for this one, we're going to wait 60 seconds.
Yeah.
And observe any changes in solution.
So it's been 60 seconds, and there's a ring around the crystals. So now you just put the lid back on and swirl, and look, turn clear. So as you can see, the equilibrium took place and shifted the other direction upon the addition of the crystals. So the solution is now fully clear. Pretty cool. So now we add one more drop of iron 3 nitrate in
One spot off the side.
one spot off to the side. Remember, not straight in the middle. So use your same clean pipette that you used for the solution. Make sure don't contaminate with any other pipette. So one drop to the side. So, like last time, forms a dark red the moment it hits the clear solution. So it goes from kind of reddish orange to a dark red. So, and don't stir, just record the color change. And now add a pea-sized amount of potassium thiocyanate crystals, one full pea size. So as you can see here, we have the same white crystals. And off to the side, don't let it make contact with the dark red. So you've added your white crystals to the side, and there's already a slightish pinkish around the crystals, but very, very light. So you should wait 30 seconds and record any changes between the two solutions that you have in the complete clear solution. So already, as you observe it from off to the side, there's the dark red from the iron 3 nitrate, and it's in a small condensed space. But the crystals, there's a slight pinkish, very, very slight pinkish color spreading out throughout the rest of the solution. So that's been about 30 seconds. So keep your lid back on and stir the whole thing. And it turns completely clear. So now you have your clear solution. That's the end of part A.
This is part B of the experiment. Our first step is to put in 10 milliliters of the part A solution into test tube A and to test tube B. Test tube A is going to be our control for this experiment. We're going to go ahead and put test tube B within a ice water bath solution, and we're going to put it in for 4 minutes.
After 3 to 5 minutes in cold test tube B of the complex ion solution, so after putting it in the ice, it's gone actually slightly darker on the bottom. If you can see that it's hazier and there's cloudiness and it's a little darker. So not like in a color dark, but slightly darker. So that's after 3 to 5 minutes in the ice. So now we're going to place test tube B in hot water. Yeah.
So we need to compare it to test tube A, and as you can see here, it's much more cloudier and much more dense than test tube A.
Yeah. So that's after cold. So now we're going to add test tube B to the hot water for 2 to 3 minutes. So we're going to put it at 2.5 minutes. Starting now. So we have moved the test tube off to the side on top of a hot plate to keep the heat constant so it doesn't lose heat.
Remember, it needs to be within 65 to 70 degrees Celsius during the entire 2 to 3 minutes.
So we're done after about 3 minutes. So here is test tube B. Make sure to use tongs whenever you're picking up hot test tubes after being heated. You don't want to burn yourself. So let's compare it to test tube A. There is slight cloudiness collecting on the bottom of the test tube, as you can see. And their bubbles have formed in test tube B.
Everything else is clear.
Yes, it is still sort of clear except cloudy at the bottom. That is the end to part B of the introduction. Okay, so this is the guided inquiry now, and this is part A, the acid-base indicator equilibrium. So for this, you're going to need your test tube, just one, and you're going to need 2 milliliters of distilled water. So
within the test tube.
Yeah, within the test tube. So we already have that there. So now you take your bromethyl blue indicator, and we're going to add 5 drops of it. It's a 0.04%. 1, 2, 3, 4.
And then 5.
We need 5.
So once 5 drops have been added, we'll swirl it and see the color change.
So as you can see, it's a greenish, it's a light green, basically. Right?
Yep, it's a light green.
Light green. So we're going to place that back there. We are done with our bromethyl blue. Now we're going to place that to the side. We're going to use that to indicate where the equilibrium shifts when we add our hydrochloric and our sodium hydroxide. Both are 0.1 molar. So we're going to start with hydrochloric acid, 0.1 molar, and 10 drops of it. So that's 10. And you swirl your test tube around. You can already see it turns a yellow color. So the equilibrium has shifted to compensate for the addition of this acid. And now we're going to add our sodium hydroxide at 0.1 molar. And we're going to add 10 drops like we did with the acid. So this is our base, remember. So that was 10 drops. Swirl it around, and it goes back, and it gets into a darker goldish color. So now what we're gonna do is we're gonna we're gonna shift the equilibrium back and forth once or twice just to make sure which side is which. So like add a little more of each to make sure the equilibrium shifts back and forth to show them.
Okay.
So let's start with adding actually more sodium hydroxide. So we're gonna add 5
drops.
5 drops of sodium hydroxide. Swirl it around, and look that you get a darker blue, so that means the equilibrium has shifted in favor. So what we're doing here, we're just looking at the effects of these acids and bases on the equilibrium. So you have your equilibrium equation, so when you add more of this side, it's going to shift to the other side to compensate and balance it out. So just to observe it one last time, we're going to add 5 more drops of the hydrochloric acid. So we added the acid. There was a quick change of gold there, but then if you keep mixing, it turns all the way back to gold, or a light green actually. It's a yellow-green color, as you can see there. So that shows you the shift of adding an acid, so it shifts back. So that's actually closer to our original color, so that shows that it's balancing out a little bit. So that's just an acid-base equilibrium, part A of the guided inquiry. Okay, so this is part B of the guided inquiry. So we're making a complex ion formation and testing the equilibrium by adding different solutions. So first you need 5 milliliters of copper 2 sulfate, and 0.2 molar. So just add that to a clean test tube. And then the reason we're in a fume hood is because we're going to have to add 14.8 molar ammonium hydroxide, which is very concentrated and pungent, so you need the fume hood for safety reasons, and you don't want to breathe this in. That's why you should stand back a little bit. So we need 2 milliliters of 14.8 molar ammonium hydroxide. It's already poured out in a graduated cylinder, as you can see here. So drop by drop, we will add it to the test tube of copper 2 sulfate and watch for a color change. That will be a complex ion formation. So remember, drop by drop and in the fume hood. So that was 2 drops, and you can already see a color change. So it turned from the light blue of the copper sulfate into a denser light blue, so it's still light blue but much denser, as you can see, and cloudier. So we are done with the ammonium hydroxide. Keep the test tube right there. Now we have 1 molar HCl. Remember to dilute it down in case you have some other concentration. So here we have about 5 milliliters, but we may not have to use all of it. So with the test tube, add 1 milliliter into the test tube of the complex ion formation. As you can already see, it turns a little clearer. So remember to stir it up. And remember to wear gloves because you don't want any of these solutions on your skin. So add 1 more milliliter of 1 molar HCl. And it becomes even clearer and a lighter blue. So this is our 3rd milliliter of HCl into the complex ion formation. So as you add it, you can even see it becomes even clearer because what's happening is in the reaction, the acid is reacting with the hydroxide from the ammonium hydroxide. So as that concentration becomes less, it becomes a lighter blue. So after the addition of 3 milliliters of hydrochloric acid in the complex ion formation, the equilibrium shifts back, as you can see. So that's all, and that's part B of the guided inquiry. Okay, this is the part C of the guided inquiry, formation of cobalt complex ions. So first what we have here are 3 solutions and 2 solutions in a compound. Silver nitrate, and you want 1 milliliter at 0.1 molar. Then you have hydrochloric acid at 6 molar, and you want 1 milliliter of that in a test tube as well. And then here we have calcium chloride, and you want 2 to 3 grains of this in a test tube as well. So what we did was we had a solution of cobalt chloride hexahydrate. So, and here's there, and you need 6 milliliters because you're going to add 2 to each of the test tubes, and each is going to react to form a complex ion, and later we're going to test it in heat and cold through an ice bath and a hot plate, okay? So let's start with the calcium chloride. With a clean pipette, take 2 milliliters. And shake them up till they dissolve. So here, if my partner would shake that up, I'll add 2 more milliliters to each of these. And if it's not dissolving, you're going to add like a slight amount more to the test tube. If it's not completely dissolved, has it dissolved?
It has completely dissolved now.
Okay, so you don't need to add any more, but that's something you can do in the future. If it's not completely dissolved, add a few drops more just to get those last particles. So we have our 3 solutions, and let's observe each.
Yep, so our calcium, it seems like it grew a little bit clearer in magenta color and became pink. Our HCl, again, grew clearer, more magenta in color. And was this one other way?
Yes.
Okay. This definitely became more cloudier, and it still has particles on the bottom.
Yeah, the particles will be there because unless you're continuously swirling it, then the particles are not there. But the moment it settles, particles appear. That's how it happens with the silver nitrate mixed with the cobalt chloride hexahydrate. So now let's move on to the heat and ice experiments.
This is a continuation of the guided inquiry, which we're using the ice bath to test the equilibrium change in each one of these, including our cobalt solution, calcium solution here, our HCl solution here, and our silver nitrate solution here. So we're going to go ahead and put it in our ice bath, all 3 of them. And we're going to observe the
color change within them.
5 minutes.
For 5 minutes, yes. So we're going to go ahead and check up on our 3 test tubes to see how much they have changed within the ice bath. We see here with the silver nitrate solution that there are white particles on the bottom, and it definitely has become a little bit more cloudy, but a lighter pink.
Yeah, a much brighter pink.
Yeah, brighter pink. Brighter pink, still cloudy. We're going to take a look at our CaCl, and this one's very interesting. You can see that there's some blue tinge on the very bottom of it, and that the rest of it is a light pink magenta. So we see that there is a little color change on the bottom. So, very fascinating. We're going to go ahead and get our HCl, and our HCl didn't change much. Still a light, clear magenta color.
Which is the expected results, because as previous people have done this lab and we have done this lab over and over, it has not had much change because the cold doesn't do much to interfere between the reactions between the two chemicals in there. So those are expected results. So now on to the hot plate. Okay, so now we're here with the hot plate, and we're about to test these 3 chemicals like we did in the ice, but now in hot plate. And you want your hot plate to be around the high 70s to low 80s. So, and once you have it there, set it to a lower temperature on your hot plate so it's at so it stays constant. The heat stays constant. You don't want it rising or dropping too much. So we're gonna take our silver nitrate, our calcium chloride, and our HCl, hydrochloric acid, and stick it in there. Make sure your thermometer is showing, and we're going to start it at 5 minutes, and we're going to see what the results are. Now, after 5 minutes, we're going to pull out our test tubes and check on how the heat has affected these chemicals. So first of all, obviously turn down your dial all the way to turn the heat off. Safety conditions. Make sure the light turns off if there's a light on your hot plate. And carefully take this beaker off and pull out each test tube and observe. So here, the silver nitrate, a lot of the chemical has, a lot of the silver has like come down into the particles, and you can see the white particles floating around. So it's actually a pink. It shows up much brighter on this camera, but particles are floating around in there, and it's a light pink. Now for the hydrochloric acid, it actually got slightly darker, just a little. It's still a light pink, but a bit of it is darker. And the calcium chloride, it's more of a purple, so that must mean it increased in a little blue saturation to become more of a purple color rather than just pink. So that completes part C of the guided inquiry, which is testing cobalt complex ions in heat and in cold and shifting the equilibrium. Okay, so this is part D of the guided inquiry. So here you have your seltzer water, and we're going to need 10 milliliters of it, so just pour it into a beaker. So as you're pouring, make sure you have exactly 10 milliliters of it. And if there's a little too much, you can always just take it out with a pipette. And I'm going to put it here in just a excess place. So be sure to have 10 milliliters of it. So it's a clear water because it's just seltzer water. So we're going to take 2 milliliters of our universal indicator, and we're going to take 2 milliliters in a graduated cylinder, a 10 milliliter graduated cylinder. So make sure to get it exactly. So cap your indicator, set it aside, and take your 2 milliliters and pour it into the beaker. So as you can see, it just already turns gold. So after you've added it in there, swirled it around, and now you have a gold color. So here we're going to take a syringe, uncap it, and we're going to pull out the solution and keep some air in there as well, because we're going to need that so we can add the pressure onto the solution. So here we're going to add some pressure and wait for a color change. So let's see what happens. And after adding some pressure, as you can see, it turns much darker. It's a darker gold. So since it's darker, it's less than the original 3.8 pH. So it's going to be a pH of less than 3, around that. So just pour it back into your beaker. And that concludes part D of the guided inquiry. So, okay. Welcome back. This is part E of the guided inquiry, and we will be testing the solubility of magnesium hydroxide. Okay, so first we're going to start off with 10 milliliters of milk of magnesia, as you can see here in the bottle. And so we have it here. You need 10 milliliters of it, so in a graduated cylinder, take it and pour it into a beaker. It is thick, so try to get most of the milk of magnesia out. You can use a clean pipette. Okay, so you have 10 milliliters of milk of magnesia. Now you need 50 milliliters of distilled water. So from a small 50 milliliter beaker, pour that into our milk of magnesia into our larger beaker. And with a stirring rod, just stir. So make sure to keep recording all the colors and all your solutions as you're going through this process. So your milk of magnesia was white, and now you just have your distilled water, which is obviously clear and no pH or anything. So after you've stirred it, it's still a milky white color. So now what we're going to do is add the universal indicator solution, and it measures a pH from 4 to 10, and you should have a pH chart a pH color chart indicating what the pH is at a certain color. So make sure to keep that handy, because you'll need that as you're going through the experiment. So, and we're going to add 5 to 10 drops of indicator, and we're going to mix it with a stirring rod. So as you can already see, it's turning a lavender color. Take your stirring rod and mix it throughout so the color is evenly mixed and your indicator is completely mixed with the solution. So now we have a lavender color, obviously. And if you look at your pH chart, it's between 9 and 10. So we're going to say around 9.7, since it's more towards purple than it is blue, rather than 9.5, which would be close enough to blue. It's more of a 9.7. So now we have to add 20 milliliters of hydrochloric acid and make sure it's 3 molar. So confirm that it's on the bottle. In case you don't have 3 molar and you have 6 or 9 or 12 molar, dilute it down by measuring the parts. So if you have like 9 molar and you need 3, you take 1 part hydrochloric acid and 2 parts water, and that'll dilute it down. But hopefully you'll have a 3 molar. So you take it in your graduated cylinder and mix it in to your beaker. You can already see a color change happen. Instant color change. mix it throughout. Now you have a light pink color, a color we've actually seen before in our other experiments. So if you look at your pH chart, it's now much closer to red, because what the hydrochloric acid does is, since it's an acid, it reduces the pH. So it's actually almost a pink now, as you can see, and the farthest the indicator goes to is a red at 4. But this is much lighter than a red, so you can say that the pH is under 4. So make sure to record your observations. Okay, so after you get your pH down to under 4, and if you want to observe the Le Chatelier's principle more by adding some more magnesium, milk of magnesia, because what milk of magnesia does is release hydroxide ions, which counteracts the acids in the HCl, and that shifts your equilibrium, and that it raises the pH closer to a more basic pH, because the acid is being negated by the base. So what I've done is added about 20 milliliters more of milk of magnesia, and as you can see, the color became more of a blue. And keep stirring, because make sure the particles are all mixed throughout. And if you look back at your pH chart, which you have, it is now more of it's between 8 and 9 now, because it's lighter than the dark blue that they show at 9, and it's not a green that they show at 8, so you can say around between 8 and 9, so 8.5. So that's just if you want to observe more of Le Chatelier's principle working throughout this experiment. So, hope you enjoyed, and hopefully you were successful. Thank you.